Today we're gonna do an optics lecture, and we will explain the generation of the non-classical light that we use in our on the optics lab. Okay. So previously we talked about that the laser laser has a photon distribution that looks like pretty much like this. It's a little bit like Gaussian, but it's not. Okay, because when the mean, so this is the mean and this is the width. When the mean get close to zero, the shape of the distribution changes. So the further it goes, the more it looks like a Gaussian. But when you go to a low average photon number, then the distribution could become strange. Okay, this is the photon distribution for for laser light, and this is called Poisson. Poisson is a French mathematician. Poisson distribution. Okay, let me just write this down. We typically call this the coherent state. Hello? We call this the coherent state, and the distribution goes like this. And that. Okay, so you can see this is the probability amplitude for the photon, for the electromagnetic field, for the field to be in a certain photon state. Okay, we talked about this in the previous lecture. Although in the previous lecture I missed a factor of exponential, so just take note of that. So this goes from 0, which is the vacuum state, to infinity. Okay, so the Poisson distribution is, so like I said, this is a Poisson distribution, but it's the probability of the photon of the field landing on which photon state. That is the Poisson distribution. So we need to take the modulus of the probability amplitude, and this will give us this. Okay. So if you check your Wikipedia, this is the Poisson distribution. People usually write it like gamma n exponential gamma. All right, so you can identify here that the gamma is alpha square. Okay. Now there are two interesting things about this. One is that this is associated with, so you see there's only one parameter in the distribution, right? and this parameter determined the entire behavior of the distribution. So the center is gamma square, alpha square, and this is alpha. All right, so the first thing you will notice is that the ratio, okay, the relative width, which is the width divided by the mean, the relative width or the percentage width decrease as you go to higher alpha. Okay, that means when this average number, when this average photon number goes to a high value, this becomes, the relative width becomes narrower. Okay, so that's one fact about it. And the other thing is, from the statistical theory, I mean, from the point of math, Poisson distribution represent events that are completely uncorrelated. Okay, so if you toast, I guess if you toss a coin and then you try to see how many heads and tails you get, or if you toss a dice, right? So you have 1, 2, 3, 4, 5, 6, and then you try to count how many times you get 1 and 2 and 3 and 4. This each throw is an uncorrelated egg from the previous one, right? Assuming nobody's cheating. In that case, I guess the distribution will follow the Poisson distribution. Okay, so this means uncorrelated. Poisson distribution is for uncorrelated events. It is a sufficient, I believe, it's a sufficient, necessary and sufficient condition. So if it's uncorrelated, it's Poisson is uncorrelated. That means for our for this photon distribution, if we try to measure the correlation in, or maybe I should say even more accurately, the self-correlation, the correlation function, the autocorrelation, yes, it's called the autocorrelation. If we try to measure the autocorrelation in the bin, right? So the array delay time, like, so in a string, let me just use dust to represent photons. So say at this moment, you get a 2 photon state, and the next moment you get a 3 photon state, and the next moment you get a 1 photon state, and then next moment when you get a 6 photon state, right? So as a function of time, as these photons are produced, they are created in an uncorrelated manner. Okay, that means the correlation here is 1, measured by our second order correlation function. Okay. All right, so this is not very interesting, right? What do we want to see in the quantum optics lab? We want to see something non-classical, something quantum, right? Quantum and non-classical are basically synonyms, because anything that you do not see in the classical world, that is quantum. So quantum equal to non-classical, okay? So we want to see something that is special. If we want to do that, then we need to find a photon distribution that is different from the laser. In other words, we need to generate light in a different way. Yeah, we need to generate light in a different way. Okay. So in our quantum optics lab, we use a method called so this is the laser. Let me just draw. This is laser, and you have light. Okay. We use a method called SPDC, which stands for spontaneous parametric down conversion, to generate a different photon distribution. Okay, SPDC. And this involves a laser. Okay. But in addition to a laser, a crystal. So this is called alpha BBO. The crystal that we choose is called alpha BBO. And sorry, not alpha BBO, beta BBO. Okay, this crystal has 2 phases, 2 tomography. No, tomology. No, that's not topology. Has 2 topological structures. On the high temperature is called an alpha phase. It's like pretty much like ice, right? When you cool the water at different temperatures, you can get ice that are slightly different. Okay, so the orientation could look slightly different depending on the temperature. So is this chemical. At high temperature, it's called alpha. At the low temperature, which means the room temperature, is called the beta. Okay, And BBO stands for baryon. So this is boron, right? Does anybody know how to pronounce this element? Boron. Boron. Yeah, boron. Okay, and this O means oxygen. Okay, so together this is called this is a compound called borite. Okay, and barium. So this is the full name is barium borite. Reason I'm not very much into chemistry, but the reason I'm mentioning this is because this bears some importance in the later discussion that we will have concerning nonlinear susceptibility. Okay, so anyway, that's just for now. Just recognize this as a crystal, and this crystal possesses some special features. And what we
it's a nonlinear crystal.
It's called a nonlinear crystal, and I will later explain what nonlinear means. Okay.
Nonlinear normally it doesn't mean like it's different topology in higher dimension. In the same temperature, it has different properties depending on.
No, that's not what nonlinear means. Nonlinear refers to its optical response.
Yes, that's what.
Yeah. Okay.
In the same temperature, it has the response with respect to its width or something different.
It has the optical response depends on the input light intensity. Yeah. Okay. So we use, in addition to a laser, something called a nonlinear crystal, and this nonlinear crystal specifically has a specific NAND type of nonlinear crystal that we use is called beta BBO. And so this is the input. Okay, the output are two light beams. Okay, they have lower energy than the input beam. So in the lab we use 405 nanometer. So that's blue. The output has a lower energy than this. That means the wavelength is longer. Okay, and of course there are many possible. Later you will see there are many possible wavelengths that will come out of this. As a matter of fact, it is not two beams. It is really a disk. It's like a cone. Okay, it's a cone. There are all kinds of frequencies that can be produced. Okay, but we are interested in A10. Okay, for the reason that will become clear later. All right, and they have symmetric angles with respect to the input beam. Okay, so this is the light source that we use in our lab. Okay, and
so
yeah,
you get a cone, right?
I get a cone.
Inside the cone is empty.
It's like a flashlight.
Yeah, but
you turn on a flashlight and then.
But inside the cone there is something.
Inside the cone you have.
Only you get a circle, or
no.
Get a disk.
Okay. A disk, and there are each position
is different intensity.
Represents, or rather the radius from the center represent different wavelengths. Yeah. Okay. So for the next hopefully hour, we will focusing on this process. What is going on here? What's the magic here? that facilitate the production of this new light. Okay, and this new light will have, as we will explain in the next lecture, will have a dramatically different photon distribution than the one we see in the laser. Okay, and here in this slide, I specifically want to discuss the nonlinear interaction between photons. Okay, that's kind of interesting interaction between photons. Okay, I'll put nonlinear here because usually photons do not interact, right? So it's really through some kind of nonlinearities in the crystal that mediate the interaction between photons. So you can also call it interaction between photons because there is no linear interaction between photons. Okay. Oh, I guess there are. Well, depends on because nonlinearity has many orders. Okay, and this nonlinearity that we want to talk about is the first order nonlinearity in the atomic response or the material response to the laser field. It's the first order nonlinearity, but as interaction for the photons is actually the first order. So I guess you can call it linear. Okay, so maybe let me just erase this to avoid confusion, right? We don't really care about whether it is first order or second order. That doesn't matter. Here we want to talk about interaction between photons. Okay, and since we're not gonna talk about we will reserve our quantum discussion for the next lecture. So today we're gonna use only classical optics or classical electromagnetism. All right, so you could also say interaction between fields. Okay, fields. That's probably a more appropriate word for today's lecture. All right.
You cannot use photons for classical, right?
Yeah, it doesn't really make sense. Yeah, I mean, a lot of people like to use that, but if you want to be accurate, it doesn't really make sense to discuss photons in the framework of classical optics. Okay, of course you can do that. Nobody's gonna be mad at you. But all right, so. So what's going on here? Right. Let me first talk about what happened to the atoms when. So let's zoom into this crystal. Let me first talk about what happened when light impinged on the lattice of atoms. Okay, let me first start with that. So, okay, so this is the crystal, okay, and these are, let me just say, okay, let me just draw a very ugly diagrams of lattice. Okay, so this is representing lattice. Okay, and then we have light coming in, and inside, this is the electromagnet. This is the electric field. Okay, I'm not showing the magnetic field, but it's there. Okay. Now, when this passed by a lattice of atoms, what do you think would happen? When the light passed by a group, a lattice of atoms, what could happen? Well, first of all, we know that atoms are charged neutral, right? So at the zero order, you might think nothing will happen. Just like when light passed through a bunch of neutrons, it shouldn't do anything to the neutron, right? So atoms are neutral. It shouldn't do anything to the atoms, right? If that would be true, then we will not have it. Actually, we will not have mirrors. We will not have glasses. We will not have anything that transmit or reflect light. We will not have that. So what really happened is that even though atoms is neutral, it is a composite entity. right? I usually will I like this picture, although this is probably not the most accurate picture of atoms that you can draw, but I think this is very illustrative. I like to imagine atoms as has a big core of a positive charge with a layer of negative charge around it. Okay, so this is like a jacket. It just that is put on this thing called nuclei. Okay. Now, when the electromagnetic field comes by, the E field will talk, of course, both the E field and the B field will talk to, the E field talk to the charge, the B field talk to the current, right? But we all know that B field is much weaker than the E field. Yeah, we have, I believe, this relation, if you remember from the previous lecture. Okay, so C is a large number, right? I think this is right? So in terms of magnitude, okay, if you check your previous note. So anyway, B is pretty weak. So we typically do not consider the effect of P if the effect of E is present. So E is the dominating effect. Now, so when we take a closer look of atoms, we see that it is a composite entity, and then it has both positive charge and negative charge. Now, both of them can move. The positive charge is basically proton, and the negative charge is electrons. Both of them can move. And they have the same charge, right? So the force that is on the proton and the electrons are all the same. Okay, both have E, right? And this is the field. However, the electron mass is 3 to the minus 30 kilogram. Oh, sorry, this is the chart. This is the electron mass. This is the proton mass. Proton mass is 27 kilogram. So there are 1,000 times, 3 orders of magnitude different, right? So that means, what does that mean? That means you have a big M. Let me just write big, capital M. Capital M means it's big. You have a big M with a small a, okay? You have a small e with a big A, big acceleration. So that means this will shake the electron and the nuclei differently. This nuclei move very slowly. It does move. So if we look at the trajectory, okay, the displacement, the nuclei is like like this, okay, it's slow. While the electron is like okay, actually I should the difference between this is actually much larger, like 1,000 times larger. All right, so while the nuclear is moving from this position to a position that is a little higher, okay, the electrons are driven up. So in the process of going up, the electrons are driven up and down many times. Okay, so this is like this, and this. So T1, T2, and T3. Okay, what does this mean for us? This means for a moment or transiently, there is a charge separation, right? The center of mass of the electron is now here, right? So you can almost draw electron. So the center of mass of electron in the steady state is coincide with the nucleus. That's why you have a charge neutral atom. You don't feel any field from the atom if you're not into the electron cloud. Okay, but when the electrons are slashing back and forth, up and down, the center of mass of the electron changes. It changes. So transiently, there is induced dipole moment, electric dipole moment. Okay, so the electric dipole moment goes from negative to positive. Okay, so you have the electric dipole moment that is induced. This is called induced electric dipole moment. And this is a function, this becomes a function of time. This is a function of time. And it goes up and down like this. Yeah? Okay. And this in this oscillating induced dipole moment is capable of producing radiation. We all heard of, if you have any previous lectures on electromagnetism, you probably heard of the word dipole radiation. Okay, there are also quadrupole radiations, high order terms, but the most common ones, how we produce radiation is through dipole oscillation. Okay, and why does dipole oscillation produce radiation? Because when dipole is made of electric dipole is made of a positive charge and a negative charge, right? And when it has oscillation, when dipole has oscillation, that means the charges are moving. And when the charges are oscillating, it has accelerations. And we all know that the electric field attached to a charge will oscillate with the charge, right? But if the oscillation is not in the form of uniform velocity, but it's in the form of acceleration, that the electric field will have the perturbation on the electric field will become a propagating disturbance or wave that goes very far, that travels very far. That's how radiations are. That's how light is made. Yeah. So we know that the oscillating dipole is associated with generation of light. Okay.
So does that means our initial laser will we get that at the center of this disk that we are getting?
Yes. Yes. All right. So it generate oscillating dipole generate light. Okay. And if we want to describe this generation process, more accurately, we need to use the Maxwell's equation. Okay. But not just any Maxwell equation. We need to use the Maxwell equation in material. Okay, the Maxwell's equation in material is a little different from the Maxwell equation in vacuum. So when you are interested in the field in the material, that field is different from the field that is in vacuum. If you have a charge, or a line of wire, a current, and then you want to calculate the field, that is the field in the vacuum, right? In the air. It's not like inside the material. But if you are interested, if you have a material, like a glass, a piece of glass, and say you have some kind of wire that is buried inside, and you or even it's possible to like put a current through a dielectric material, not just metal, but that is possible. Like for example, semiconductor, it is possible to put a current through a dielectric, like silicon, put a current through a dielectric material, and the field that is generated is born inside the material, and then it will come out of it, right? So it is, of course, of interest to understand how field behave in materials, and that's why we have this Maxwell equation in material. Okay, so this is a little more advanced version of the Maxwell equation. And so in order to understand the radiation generation process, we need to use the Maxwell equation. But also another reason we want to discuss this is because if you remember our quantum optics lecture last week, we talked about like where does the quantum part comes in, right? And we talk about like there are many aspects of the field. You have polarization, you have mode function, you have frequency, you have wave factors, you have photon numbers, right? It is the photon number, or sorry, you have the amplitude, right? It is the amplitude that gets quantized, right? And the amplitude, the amplitude does not grow in a continuous manner. It grows in the discrete manner, just like the energy for atoms. It increased in the discrete manner or quantized manner. And so we said that the rest is determined, it's the same as the classical electromagnetism tell us, yeah? So one of that is the mode function. One of the important things is the mode function. The mode function, or you could say the distribution of your intensity, okay? Your intensity distribution. How does your light look like? You know, having an intensity that is brightest in the center, and then it's like a round shape, or does your light, I don't know, it's like very narrow and it has like, sorry, does your light have like a little disk in the center and you have rings around it? Those are called the mode function. The intensity distribution is really the intensity. So experimentally, it's basically just the intensity distribution. Okay, how are my energy distributed? How my energy distributed? Okay, and for plane wave, of course, it is just spherical. This for plane wave, it is just this, right? So this is like a spherical wave that goes out. But you can have Fourier transform. You can have a summation of frequencies or a summation of wave factors, and this can give you a more interesting mode function, such as a diffraction pattern, a single slit diffraction pattern. If you put a pinhole or iris before in the beam path of laser and you close it, you'll see that the laser goes from a Gaussian profile into an airy ring. Okay. So this is like, I would say this is more like KR and KR, like that. Okay, so it's more like this. All right, so the Maxwell's equation determines the mole function, and so it is important for us to. So if we want to understand this light, we not only need to understand how the photon distribution changes, but we also need to understand how the mole function changes. Okay, so then that's why it's important for us to. It's unavoidable for us to discuss the Maxwell equation. Okay, so let me just quickly write down the Maxwell equation in vacuum is. How many of you can remember Maxwell equation by heart? I should put that as a quiz question. Huh? So we have 2 curls and 2 dots, right? That is the easy part. Okay, and then we have 0 for this guy. 0. So this is the poor guy. He has 0, but the rest are not 0, right? Yeah. Okay, and we know these are related to the induction, right? These are related to induction. If you have the oscillating E field, then that will induce, or if you have a change of E field, that will induce some B field. And you have a change in B field, you will induce the electric field, okay? So these are associated with the change of the field of the other kind. Yep. Now, the tricky part is that's why a lot of people goes with Gaussian unit, because in Gaussian unit you don't have coefficients. You basically have no parameters in the Maxwell equation. Okay, but I hate Gaussian unit. It's so confusing. All right, so I'm going to stick with the pen of this unit, and then here it is U mu E naught. Okay, and here it is minus 1 over C. Okay. So these are the field induction as source for the field, or the change of the field as the source for the other kind of field. Yeah, I told you these two are 2 sides of the same coin, right? So if one side something happens to one side, this will affect the other side too, because it's really affecting the coin. All right. So this is how the field will make the other component change. But we also have the materials, how materials can affect fields, right? And we have 2 types of material, one or matter. One is charge and the other is current. Okay? So charge is associated with this is charge density rho. Charge is associated with electric field, and current is associated with the magnetic field, right? And everything we write here regarding mass, regarding matter is in terms of density. Okay, so we're looking at the building blocks of a material. So that's how the equation is written. Okay, so if you have like 1,000 atoms, this is like the atom density. Okay, or if you have like 1,000, I don't know, if you have like a charged cloud like this is basically the density of that electron cloud. Okay, and this is the density of a current. So if you have a surface current or volume current that goes either on the surface of a material or inside the material, we're talking about like the unit of it. All right, so that's the Maxwell's equation. All right, in vacuum. Now, for Maxwell's equation in material, we have two extra terms. Okay, we have two extra terms, and that two extra terms originate from the response, the optical response. Okay, we call it optical response. It's really just the electromagnetic response of the material, how they respond to the field. Okay, and these two are, as you can imagine, one is related to charge and the other is related to current. So in pretty much the same form. Okay, so in the material we have polarization. Okay, and polarization is basically just so if this is for a single, if this is dipole moment for a single electron and proton pair, you take that and times the density, which so n here represent the density. Density number. Okay, so it's the density, atom density. Okay, let me just call it atom density. Polarization is the density times individual. How many atoms you have per unit volume? That's n, and times the dipole moment. That gives you the p, the so-called polarization. Okay, polarization. So we have this thing that is basically charge, the charge response of material, and we have the other thing called m. Okay, and maybe as you can imagine, n is basically just n times the magnetic dipole, or the induced magnetic dipole. Okay, all right. So p is this, n is this. Okay. Now today we're gonna focus on n, p, but I'm gonna give you the complete equation. So we basically have two extra terms. One is here, and the other goes here. Okay. Yeah. Let me see. Okay. So this definitely changes. Okay, because the material response changes. But in addition, there's a little asymmetry here. We also have this term that will be changed, but not this term. Okay. All right. So this is pretty interesting. So let me write it down. So this term does not change. So let me just keep it the same color. Okay. But this will, oh, give me a second. Yeah, this will change. And if this, so what really changes is on this side. Okay, but if we define a new vector that include the field and the new term, we can make this new equation in the form that is very similar to its original form. Okay, and similarly, it goes with the B field. Okay, if we take the B field and then just attach it with a new term from the material response. Okay, we could basically put the changes from this side, include the changes from the other side to the field term, so that it will look like this. J has okay delta d dt, and of course here this is 0, so there's no point to change it. It just remain the same. Okay.
In the first equation, del cross E, so speed of light changes in the medium, right? Speed of light changes with respect to the refractive index, right?
Yeah.
So why is not that considered?
Yeah,
eta by n or something.
Yeah, you'll be considered. You'll be considered.
It's in the first equation. It's the same. Right?
No, you will see. You will see. Well, first of all, you see that there is no material. All the material response are represented by these coefficients. Okay. Here you have only the speed of light.
Yeah, but that's
but
C,
no.
C equal to 1 by
No. This is independent of the material. So even in the absence of material, this term is still there. Okay, so that means this term, for some reason, this term just doesn't. This term is not affected by the material. If you remove the material, it is there.
Yeah, means if there is no material, so you get like C equal to 1 by mu 0 0 0.
Yeah, let me just continue, and then you will see. All right, so here we have the Maxwell equation in material. And why is this? Why I go through all this trouble to explain this? Because let me jump back to. So we have this, okay. But before we can go further, let me jump back to the interaction between the field and the atom. Yeah. Okay. So I just gave a picture of the field driving the atom, and for effectively can just see the nuclei as stationary. It's not moving, since it's moving rather slow relative to the electron. So we can only we can just only focus on the electron motion. This is called the Born approximation. Okay, so let's just focus on the electron. Okay. Now, this is really ugly. Okay. Now, for the electron, yes, like we said, the field will displace the electron relative to the nuclei, right? How far? Question is how far? if you have a strong electric field, that means you have like, you crank up the intensity of your laser, a large photon flux, right? In quantum mechanical terms, that means a lot of photon flux. The average N is large. What will happen to the electron? Does it get to go like infinitely far away from the nucleus? If we keep increasing our laser, we could do that. We can be pretty strong laser, and we can just burn, for example, a quartz with it. Yeah. So of course, yeah, at some point you'll reach something called the radiation damage threshold, and you will literally burn this thing. Okay.
Is it ionizing the?
Yeah. You literally burn this thing. Things falls apart. But that requires really high intensity lasers. Okay. But right now, we're not into the business of destroying our equipment. So right now, let's just say if I continue increase my field in a reasonable way, what will happen to the electron to the distortion of the electron cloud? I would say that the displacement or the distortion will become less and less responsive to your increase of field intensity. You see what I'm saying? That means, so if I have like 1 unit of field, and that give me, just say 1 nanometer of displacement in my electron cloud, right? Okay, now I increase this to 2 units of electric field. Then I get 2 nanometer of electron displacement in the cloud. Yeah. But if I keep going, if I go to 10 units, do you expect I will get 10 nanometer of displacement? What I just said is, no, it will not. It will become less and less effective in displacing the electron cloud. Okay, so as a matter of fact, when you go to 10 units of electric field, you probably will only get a displacement of, say, 6 nanometer. And when you go to 20, you get not a lot, you probably just get 8. Okay, so it's kind of strange, right? The harder you drive it, your drive becomes less effective in displacing the electron cloud. Why is that? This is a really hard question. Huh? The question is, when you drive harder and harder, right? The drive becomes less and less effective. Not that it will not produce any effect, it will still move it, but it's not move it as much as you would expect, as you would hope, right? If I give it, like, if I double the drive, I should see double the displacement, right? But in fact, I don't. I see probably only like a 20% increase in my displacement. Why is that? So I know I'm stating that as a fact, but what is the reason for that? Those of you who love computers, do you have an answer for me? Does your computer tells you? Think about it. Of course, you can continue with your computer work. That's no problem. But I'm just asking you if you would like to take a minute break from your computer and think about this question. What would be your answer? Why, when you drive it more, it's actually become less effective? I would suggest that you look at this picture. Okay, this picture provides a clue.
You
Alright.
need more force to separate them.
Huh? Say again?
You would need more force to separate them.
Why? Why? Yeah. Why more force? Where does that come from? Okay. Well, let's just think for another 10 seconds, and I'll give you the answer. And after that, we will take a break. Okay. So if you have learned even electrostatic. But well, actually, that if you consider the spatial dependence of the electrostatic force, it actually will make your drive more effective, because the further you are away from this, right?
Less force,
Yeah, the force is weaker. It becomes weaker and weaker.
Yeah.
And it's easier to, like, if that's what's going on, then you won't need much increase. Then you can like really take it, right? When you launch a rocket to space, you don't need more and more force to pull it out of gravity, right?
Is it because there is other atoms are coming near and the negative force repulsions?
No. Just consider a single atom picture would be sufficient. Yeah. All right. So the reason is,
Conservation of momentum?
sorry?
Is it deal with conservation of momentum?
No. Okay, so what?
I mean, you can look at the displacement.
Uh-huh.
On this.
Yeah.
And that should be, I think there's a wrong side on the correct.
No. The answer has nothing to do with Maxwell's equation. All right, let me give you the answer. The answer is this. Okay? So when you are displaced a little bit, right, there's still a large portion of your electron cloud surrounding the nucleus, right? And this shield the positive charge. So the pulling, the force, the restoring force that is pulling you back. We've been focusing on the electric field of the field, but we have not really considered the electrostatic force from between the charges, right? Okay, so if you just consider this and this center of mass of the electron cloud and the nucleus, you see there is a restoring force, right? Yeah, and this restoring force is determined by it's largely determined by this positive charge cloud. Yeah. So when it was like this, of course, you have the same amount of negative charge surrounding the positive charge, so it's charge neutral. But right now, like here, when this are pulled out, this layer, this jacket becomes thinner, so you have less charge in around the nucleus, right? And so you have you start to have a net positive charge, and that provide a restoring force, right? Now, when you drive this further, when the electric field drive this further, like this, for example, I'm exaggerating.
Because of dipole.
This jacket becomes really, really thin, right? So this is, let me say, if this is like positive 5e, okay? Now this becomes positive 20e, right? Because the jacket, the shielding layer becomes thinner. So when you go further, you will feel a stronger and stronger electrostatic force that's trying to pull you back. Okay, so it becomes stiffer. So if you think of this as like a spring, right? The spring does not become weaker as you pull it forward. The spring actually becomes stiffer as you pull it further away. Yeah. So if I would draw the potential as a function of displacement, okay? Actually, I should draw here. So instead of a parabolic potential, which means your restoring force is linear, right? You have as much restoring force as your displacement goes. Now you have a steeper, right? So that in this, so we know the force is the slope of the potential, right? So this is not a great drawing, but in principle, the force should be the same. The slope should be the same at any point of this parabolic potential, right? That will be a linear spring, a linear response. But right now, because of this shielding effect, becomes less and less, it's weakened. So when we are here, we have this, but when we are when we are further away, like here, the force is increasingly stronger, significantly stronger, okay? And when we go a little further, it is like even stronger, okay? So this is called a nonlinear response or the nonlinear regime, okay? And this is called a linear response. Yeah? Okay. So you see, the stronger you drive the atom, the more nonlinear the response becomes because of this weakened shielding effect. The shielding effect is weakened. Okay. All right. So we will take a break here, and we will convene in 5 minutes, and we'll continue our discussion on this. Okay.
But you still don't lose any energy. It just that it doesn't get out more.
Yeah. It's basically a spring that becomes stiffer as you pull it out.
It's not like you get heat loss.
No.
It gets stiff.
Yeah. It gets stiff. Yeah. I don't know what will be like a daily life analogy for such thing. Like the further you pull it, the stiffer it gets.
Rubber.
Huh? No.
Rubber band.
The rubber band is linear. The displacement gets.
You need more force as you go.
Really?
It's easier to make small displacement.
That is due to the displacement. The spring coefficient is still the same.
Yeah. Of course, yeah. If you need more force as you have more displacement, because force is proportional to displacement linearly. Okay. You need if you pull it twice as far, you need twice as much force. That's okay. But I'm talking about like if you want to pull it twice as far, you need like 10 times as much force. That's a different. That's what I call nonlinear response. And I don't know if there is a daily life example for everyday example for this.
det så att det kan vara väldigt smalt, men om det faktiskt är så pass långt plats att det hinner uppnå återställning till så.
Kommer det verkligen vara mättat där? Kommer inte jag ha tiden?
Ja, det är ju intressant att det var lite relaxation time. Men relaxation time kommer att vara en millisekund range. Medan en sån här lightweight puls är kanske bara 200 nanosekunder eller 500 nanosekunder. Eller 900 nanosekunder kör vi ju.
Ja, men här. Den är det.
Så jag vet att den här brukar jag köra mellan det är ju bara nanosekunder. Det är betydligt kortare. Men sen hur mycket du behöver här emellan, det står ju i...
All right.
Det står i lammarna och jag tror det handlar om mikronanosekunder. Inte det tillräckligt långt som ska vara
Nej.
en större mängd.
Nej.
Kolla.
Let's get back to this. All right, so from our discussion, we can see that basically our displacement or the electric dipole moment, which is of course Q and X, right? So just charge, not unit charge, but just whatever charge that is exposed. Yeah. The net charge that is not shielded. So charge times displacement. Okay, and this is our displacement. Okay, and this is our charge. D is this. So this is basically a function of our input electric field. Yeah. But we know that we don't know the functional form of this, so we're going to give it a general form. Okay? And the general form is basically just a Taylor expansion. So one coefficient, this is the first order, this is the second order, this is the third order. Okay? So this coefficient here also include the units, take care of the units. So we know that this is not, do we stop at the first order? No, because we know that the nonlinear effect can make the displacement not just linear, not linear with the your if this will be true, then basically this is the force, this is the displacement, you have the spring, right? But we know that this is not true. When you drive it harder, it will respond nonlinearly, and then therefore we will include these terms, and we call this the nonlinear optical response. Okay. Now we know that polarization, as we write here, polarization is basically the same as the dipole moment, but times the density, right? So the same dependence on the field will also goes with this, okay? And so you see here, P and epsilon naught has the same, epsilon naught E has the same unit. So here you can write epsilon naught E X1. So this is a uniless. This is a dimensionless. This is a dimensionless expansion factor. This is called chi. You can write something like this. Yeah? This dimensionless explanation factor, we call it susceptibility. Susceptibility. This is really mouthful. Anybody can pronounce this really fast? Susceptibility? Good, good. Yeah, yeah, it's very difficult. I don't know why they give.
What is the inverse of the susceptibility? It's something crazy.
Yeah, it is.
Okay. All right.
That's epsilon.
Okay. So this is called susceptibility, and this is related to what we know as. So this is vacuum permittivity. Vacuum permittivity. Okay. Okay. So the vacuum permittivity carries a unit. Okay, and susceptibility does not. All right. Okay. And here is the relation. So the relative vacuum permittibility. So this is the relative vacuum. So I'm just relating our discussion here with the terminology that people usually use. Relative vacuum permittivity. This is related to this. To this chi by just acting 1. Okay, because 1 represents vacuum. So if you have no mass, no material, this is out 0, then you have, right? Okay. So this is how people usually call it. And this is also related to something that we will discuss in a bit. This is also called, I believe this is called also dielectric constant. So, okay. Dielectric constant of materials. Okay, each material has its own dielectric constants. Okay, and the dielectric constant is related to the index of refraction, n by square. Okay, so here you see n is related to this series of coefficients, this expansion coefficients. Okay, all right. So it's something to. This is something to keep in mind. This is background knowledge. All right. I want to point you to something else from a mathematical point of view. You see, this is a vector. This is also a vector. So vector and vector are related by a coefficient. No problem, right? Now, this is strange. What is the square of a vector? Dot product? Curl product? Huh?
Dot product?
If this is a dot product, then the result will be a scalar.
Yeah.
That will not be a vector, right? So this is kind of strange, right? Here, this is even more bizarre. You have a cube of a vector? What is that? And how can a cube of a vector give you a vector? All right. So just even from a mathematical point of view, this is kind of strange to write it this way. Okay, but I write it this way just to show you like how this is really originated from the nonlinear response of the dipole moment being induced or pulled by the electric field. All right, so dimensionally this is correct. Okay, but when we put it in the vectorial form, this is very strange. All right, so this reveals something that is actually pretty important. This thing are not as simple as we imagine they are. They are not just scalars. These are called tensors. The susceptibilities are tensors. Okay? Let me write this down. So the correct way to write this, the correct way is write it component by component. So this component I is related to this component of E by a matrix. Okay, so this is 1D, this is 2D. Okay? So even in the linear response, we have a matrix. Okay? And here we have square, right? So that means J and K. Any pairs of the electric field components, the product of any pair of electric field components related to this by a specific coefficient ijk, right? And as you can see, this is 2D. This can form a 2D matrix or a row vector, like depending on how you want to. If you want to write it as, let me just keep it pretty straightforward. 2D and this is 3D. Okay. And for this, you have J, K, L, yeah? And this is, of course, I, J, K, L, right? This is 3D, and this is a 4D, and it goes on forever, okay? And of course, all this, in front of this, we need to have the summation of all I, all J. Here is the summation of J and K. So all pairs need to be considered. All pairs need to be considered J, K, L. Yeah? All right. So that's what's going on, okay? All right, so this is pretty messed up, right? You have a 2D mathematical object that describe the nonlinear response. Like, how do you go about calculating this at all? Okay, well, later I will show you how you can practically do it, but let me first explain what this means physically. This means, so the components of E represent the electric field in different directions, right? X, Y, Z projections, okay? So when the field is inside the material, it points this way, and with respect to the crystal, you can of course put a coordinate system on the crystal according to its crystalline structure, right? So a 3D crystal, you can define, just like people in condensed matter would do, they can define A, B, C, right? A axis, B axis, and C axis. Or if you like, you can just define in the most generic coordinate system, the Cartesian coordinate system, X, Y, Z, and they are all perpendicular to each other, right? So So if we just do that, instead of going by the crystal coordinates, if we just do a generic XYZ coordinate inside of each material, then this means the material response in the X direction, okay, can be determined by the E field in the XYZ direction together. That's what this first term means. The XYZ polarization, the XYZ polarization projection can all affect the material response in the X direction, and so goes with so goes with Y and Z, yeah. And this, of course, if you understand what this means, this is not hard to understand, right? So this is the pairs of, the first field in the X projection and the second field in the Y projection, and together somehow they have an influence on your material response in the Z direction, okay, or X direction. So that just goes like this, okay. Now mathematically, if you're interested, mathematically you can write it. So you don't really need to construct this as a 2D object, okay. This is basically a tensor product, okay, and you can do this instead of having a row. If you do a row vector in tensor product with, if you do a row vector tensor product with a column vector, yes, you will get a matrix. But you could also do a column with a column, yeah? And that way you just get a longer column, yes? And here, you always have a column vector, right? So what relates this column with this big column with this small column is just a matrix that is square, that is rectangular instead of square, right? Yeah. So square means this and this are the same size, but that's just what a square matrix means. But if you have just a matrix that does not have same dimensions on both sides, just have a rectangular matrix, that can totally characterize this thing. So you can put this into like this, a square, a long square matrix, okay? And this will be just a dot product, okay? Yeah. And of course, the same goes here. Here, this is kind of trivial. You just go with a column vector, and here you have a square matrix, okay? And here, the same trick you do here for the second order, all right? So all of them mathematically can be cast into a 1D mathematical object with a 2D coefficient. But nonetheless, at best, this is a 2D mathematical object, and that is the tensor root of it. Okay, that is tensor root of it. That means the material response can, in principle, be very different in different directions, x, y, and x and y. Yeah. So that's something you need to know. You will not need to be bothered with this forever. I don't think you will have to, unless you're like hardcore nonlinear, like doing hardcore nonlinear optics, and you have to do like first principle calculation. Then you will have to worry about the matrix form of this. Otherwise, you don't need to worry about this. But I just want to bring this to your attention because this is actually a very great example for tensors. We don't encounter tensor objects very much in physics. This is probably the first instance. If we understand this, Then later, if you want to learn, I don't know, spatial general relativities, yeah, they use tensor a lot, and there you know how you're not like too scared with tensor. Now you know like how to operate them, at least at the mathematical level, right? So that's cool. That's all good. All right, now I want to.
Is this tensor symmetric?
Huh?
Is this tensor symmetric?
That is not guaranteed. It depends on the material and the crystalline structure. Yeah. So regarding the symmetric property of these tensors it varies from material to materials. That's why we have sometimes a special choice. It's not like just can take any material. Of course, every material has this nonlinear crystal response. Yeah, it's just a matter of large or small, right? But also the crystal structure also matters. That affects the form of the tensor. Okay, so that's why we choose. If you look at the catalog of all this optics vendors, there are not many choices for nonlinear optics, nonlinear crystals. Beta BBO is the most common one. The next common one is the lithium niobium boride. Okay, so there are just maybe 3, 4, a handful of them, just a handful of them that are useful.
And also these 2D, 3D, 4D tensors are like independent, right? It doesn't have any dependence.
Oh, you mean from this to this?
Yes.
No, yeah, they are independent. Yeah, they are on its own. All right, so having told you this much, okay, having told you this much, the reason I wanna give you like all this introduction is because I want to do the following thing. Okay, I wanna all right, let's just remember that this has a perturbation expansion. Let's just use this notation for now, for simplicities. Okay, I don't want to write Maxwell equation in component by component. Okay, let's just write this, but with the knowledge that knowing that this represent this. Okay.
One more thing, like in that equation, susceptibility is like a number, right?
Which equation?
In
Here?
Yes.
Yes. Yes. So say we have a certain symmetry in our tensor, in our susceptibility tensors, and it can all be reduced into a number, a single number that characterizes.
So you use that number to get the dielectric constant.
Right. Yeah.
Because you cannot have a matrix inside that.
Right. Yeah. In the most general form, yes. If these are tensors, this is going to be very complicated. Okay. Yeah. So like I said, there are materials with certain symmetry properties, and here we're assuming that the material that we use have a special symmetry property, so that all these tensors can be reduced. Of course, it has its, like 1 and 0 here and there, but it can be reduced into a number. Instead of having like 9 different numbers, we have one number.
I think also some nonlinear materials has like in different direction, different refractive index, right?
Yes.
So that's also because
reflected here. Yes.
Because if you're considering that direction, the susceptibility will be different depending on the tensor.
Right. Yes. Okay. All right. So, but just for the sake of brevity and simplicity of our discussion, as we will use this form with the knowledge that this means this. Okay. All right. So right now I'm gonna go back to our All right, we don't have much time. I'm gonna try to finish this in time. It's just pretty impossible. But I don't want to go for 3 hours again. Okay. All right, so give me a second. Okay, so I want to start with this. If we have only the linear response, okay, that means P is equal to E, right? Then our D, as we define here, I'm gonna focus on the electric field from now on. Okay, this will be this, right? And you can group the coefficient like this. Yep. And you can call this a new permittivity in the in the material. Okay. The same you can do with the edge, and so if you have the linear response of M, okay, let me just write M as I don't know if there's a good, let me just use kappa. Okay, let me just use kappa. Oh, no, let me use eta. Okay, let me use eta. Okay, so the same story, the same game we play with the dipole moment, you can do it with the magnetic moment. And so in this case, this will be eta. Okay, eta. Oh, sorry.
It's 1 by
right? This is dimensionless. That's just as this is dimensionless. So you can really just define, rescale your vacuum permittivity to, instead of mu naught, you can do mu. Okay, then do this. All right, so if you do this, your Maxwell equation resumed to its original form. But just with the difference in the constants that pertains to the materials. Okay. Mm-hmm. Okay. So you see, there's all the constants that pertains to the materials are now replaced by the permittivity and a permeability, right? I think it's called permeability. Okay, permittivity and permeability in the material. Okay, so in the vacuum, you have epsilon naught and mu naught. In the material, you don't have that naught. You just have epsilon and mu. Okay, so this is pretty much like, so for the linear, if you assume linear response, you get the same form as in the vacuum, but just with the material constants, the constants changes to the material ones, okay? And of course, here you have, you can derive the wave equations. Sorry. Like this, and you also have a wave equation for B. Okay, so let me focus on E. Yeah, and you can see that here the speed of the wave. So this has the unit. So this is 1 over x, right? And this is 1 over t. So this is the speed of the unit. Actually, speed of the unit square, right? So the wave in the material have the speed of mu times e, while in the vacuum, in the vacuum you have the vacuum speed of light, mu naught e naught, okay? And of course we know that n is V is C divided by n, okay? And in this case, we typically assume that there's not much going on in the magnetic field response, so this remains the same as the vacuum value. So that's how this is related to the dielectric constant. Okay. Okay, so this is how it works, and that's great. And this linear response, you can see that it ends up giving you this parameter called the index of refraction, and this is responsible for a lot of optical effect, right? Okay. All right, so let's just say this is all good. But what happens if the response is nonlinear? Okay, what happens if the response is nonlinear? Okay, in that sense, does the equation becomes untrackable or very difficult, or what? Okay, lucky for us, the wave, of course, this will become pretty cubism. But lucky for us, the wave equation. So the wave equation is assuming, of course, no charge. So in the presence of no external charge and no external current, we have the wave equation, right? So the wave equation, I will go without derivation. The wave equation in this case, if you derive it, if it's nonlinear response, then the wave equation is actually not too bad. So this is the general form of the wave equation. Okay. This is pretty important. Why is this important? You see, now this characterized the temporal change of my field. And if there are nonlinear terms of V in the P, this also characterizes how the interaction between different fields affect my field. Okay, so this is actually a very important equation that is derived from here. Okay, all right. So, but you need to do a little math yourself, and of course here, P could be exponential IE and let me just write E squared, okay? With the knowledge that this means the tensor product. E and IE squared. Okay. Okay, and now, so if we limit ourselves to the second order, then this will give us equation. Let me see. Oh. This will give us two terms. So there are two terms, okay? And this will change this equation to the following. Assuming we have, right, here we just assuming that the magnetic response there's no magnetic response, we ignore that, okay? Yep. You see how this is changed to the dielectric constant, to the linear dielectric constant? Okay.
So
but
for the dielectric constant, we only consider the first term?
Yeah. So this is a regular thing. Okay? The regular dielectric constant, and that is related to n. Okay? Because like the contribution of this higher order term to n is really small actually. Okay? And here you see that this is an interaction term. This is an interaction between fields. And this is what we mentioned at the beginning of our lecture. We want to know what's going on with the field, okay, inside. Okay, that almost done. Oh, right here. Oh, I forgot to write. This is 4, right? Yeah.
5, right?
Wait, is this
5.
5? So I erase 4.
Yes.
Oh, thank you. I erase 4. Okay, thank you.
Because you didn't erase this side and erase that side.
Okay, okay, good. Thank you. Okay. All right, so that's the equation of motion, and this E is the total E field. Okay, so for our, so this is 6. For our earlier discussion, right? So we have, remember the crystal, and we have an input field, yeah, which we'll call EP, pump. And we have 2 output field. So they are interaction. The interaction occurs inside the crystal. The field goes into the crystal, there's interaction, and it generates 2 output field, and the field leaves the crystal, right? So we call this E1 and E2, okay? And while they are in the material, we are gonna use that equation. Okay, so this total field here is E1, E2, and EP. Yep, okay. So you can imagine that I can, I mean, the left-hand side is pretty linear. So there's E1, E2, and EP. And the right-hand side, we have product terms, okay? And for now, we will assume that EP is so strong. Okay, this is, I think it's called, this is called parametric excitation, parametric approximation, parametric approximation. EP does not change by the interaction. Okay. So that means that just means in the EP equation, we kill this term, we ignore this term. Okay. For the sake of this discussion, when we are doing second harmonic generation, then that's not the case. We will we will not do second harmonic generation here. But if you ever deal with second harmonic generation or third harmonic generation, then this EP equation is actually the main equation. And you will assume that the rest of the field are not changed. Okay, so basically whatever is the input field, whatever is used as the input field. So this is the input. Whatever, so this nonlinear process you could have two field come in and one field come out, or one field come in and two field come out. There could be many processes. There are a lot of possible processes, but most of the time we just assume, because the input is usually strong and the output is weak since it's the nonlinear, right? The nonlinear coefficient is weak, is small. So usually the output field strength is small. So we would almost always focus on the time evolution, the dynamical evolution of the output field, and just assuming the input field is intact. Okay. EP is intact. EP stays intact. Okay. So here we can write equations for E1. Okay, so there are here a lot of terms. A lot of timers. Okay. Now, so these are the equations that we will use. And here, in principle, you have 9 terms, correct? So you have E times E, right? E tensor product with E. So you have 9 terms, right? 1, 1, 2, 2, PP. 1, 2, 1P, 2P, and then like just 9 terms.
It's not symmetric.
Okay? So you have the cross terms, you have the self terms. Now, which terms are important? In nonlinear optics, you will find that actually, often in a lot of times, there are like just so many terms, but only one is important. Because there's only one term in terms of magnitude dominates, and in terms of frequency is resonant. Okay? So let's just do a little guess. So out of all these terms, 9 terms, okay, let me just write it out. 1, 1, 2, 2, EP, right? And this is 1, 2, 1P. And this is 2, 2, 2, 1, and 2P. And this is, what else?
Right, in terms of matrix, that's still better.
Huh?
2, 2. Then there's
I think this is everything. Oh, actually, I think there are only 6 terms that are, distinct, and these are just
symmetric,
right?
Yeah.
Okay, so they are really just like 6 unit terms. Okay. What would you guess if I can put one term here? Which one? Oh, sorry. Let's just say if I can if this is too small for 6 terms, if I have to leave some out, what will you leave out?
The cross terms.
They are all cross. Okay, you have the self term, you have the cross term.
Self term will be resonant, right?
You will keep the self term. what will you do?
Yeah.
So these are the self terms. Okay, and these are the cross terms. You will keep the self terms. What will you do?
Self-term.
You will keep the self term. Everybody likes self term. I don't know why. What will you do? Just make a guess. Huh? You will keep the cross terms? Okay. What I would do is I will go with terms that has P.
Yeah.
Because P has the strongest magnitude, right? So I will go with these terms first. Okay? I will leave out terms that has no P, because I know these are dominant terms. Okay? And next, what I need to consider is, it's not clear here, but it will be clear later. Next turn, I will consider resonance. Okay? These terms are basically frequency mixing terms. This is oscillating at omega p. This is oscillating at omega p. So when you take a product of that, you have omega p plus omega p and omega p minus omega p. Right? So you have 2 omega p and 0. Yes? And here you have what? Omega p plus and minus omega 2. And here you have omega p plus minus omega 1. Yes? Okay. In order to be resonant with omega 1, okay, so say you have ignore everything else, just say, like this term is really similar to Newton's equation, right? Okay? So say this there, so this is also omega 1 is E1 is oscillating on omega 1. So if you want to produce a term that can be resonant with omega 1, what will you choose out of these 3 terms? What will give you the best chance? I'm saying that a word, but what will give you the best chance to have the mixed frequency matching S drive match? So this is you can see this as like an oscillator, and this is a drive. Okay, what will be the mixed frequency as the driving frequency? That will be the resonant with omega 1.
Even square.
Even square? But I already leave that out. You mean this one? I already leave that out. And by the way, the frequency component in this one is 2 omega 1 and 0. Okay? The frequency component here is 2 omega p and 0. Frequency component here is omega p plus minus omega 1, omega 2. Here is omega p plus minus omega 1. Okay, so I have write it out for you. What would you think that has the most chance to be resonant, to match omega 1, to be equal to omega 1? Just let me remind you that these are all large numbers like terahertz. Okay, omega p is terahertz. Omega 1 and omega 2 are also at the order of magnitude of terahertz. Yeah? Right. Is it this one? No, obviously not 0. Right? Omega p? Could be 2 omega p. If 2 omega p is resonant with this, then that means this will be a lower frequency, and this will be higher frequency, right? This will be the case for second harmonic generation, but not in our case. Here we're talking about down conversion. So the output frequency is lower than the input. Okay, so obviously this will not work. Okay, so it takes a higher frequency to even higher. Yeah, how about this? It's 2. So omega p is like here, okay, and omega 1 is like somewhere here, somewhere around at the center of the magnitude. Okay, if you take like this much and you add this much frequency to this frequency, then you have like here. And if you subtract from this frequency, you have like here, almost 0. Okay, so you have either very high frequency or very low frequency, similar to this. Okay, so this won't work. Yeah. Now this one, maybe. Okay, because now omega 2 is actually you can put like the game we just played, right? So if I want this to be the same as omega 1, right? Then omega p will either be 0 or 2 omega 1. Okay? And this is not crazy. This is possible, but they need to be very different. The frequency need to be very different. Okay? But how about here? If omega p plus minus omega 2 is equal to omega 1, then omega p is either the difference between the two or the sum between the two. Okay? The difference between the two, it's possible. Okay? The sum of the two is also possible. If this is possible, then
yeah, like that we can write the other one also like omega 1 by 2, right?
Yeah. Yeah, so this is like a special case of this.
No, I mean the other one.
The other one, which
E1 EP. If you use that, we can write it like omega p equal to omega.
Yeah, that's what I write here.
Okay.
Yeah. 0 and 2 omega 1. Okay.
Okay.
And this is a special case of this.
Yeah.
Okay. So I will go with this term. Okay. It seems like both terms could work, and this also includes this special case. Okay. So I will go with this term. Okay. And the same again, you can play with this, and then here by symmetry, you know, it is omega 1 times omega p. Yeah. And this is whether this will work or not, well, you have to work out the equation to the very end to see. Okay. But I can tell you that this is the right choice. If you want to be safe, you know, you can include both terms to begin with, and see which terms survive in terms when you consider resonant conditions. Okay. All right. So that's basically let's do this. Okay, so what we're doing here is that we are writing just the fundamental wave for frequency E1, for frequency omega 1. And it's amplitude, and its amplitude F. Okay? And we'll do the same for E2. For its amplitude F. So this is F1 and this is F2. Okay? So if we do that, then we can see that this equation now becomes E1 I'm gonna keep this. So the purpose of writing it like this is because I want to get rid of this is also a quite general form because we're concerned about the amplitude, how the amplitude of E1 and E2 change with time, right? But the main purpose of writing this out is to just get rid of this derivative. So I will keep this the rest is the same. Okay.
And f of t is the amplitude.
Right. Yeah. F1 of t is amplitude. F2 of t is amplitude. Or you can say the envelope function. Doesn't matter. It's just the amplitude. Present the amplitude, and I'm going to use a little different notation. Okay. So this is omega. This is V1. Okay. Now you see, I could put this to here. V equal to C, sorry. In the material, you don't have omega equal to CK, you have omega equal to VK, right? So this term can be combined with this term. And so you have only the time derivative here, and then you move this term to the other side. Should I have a minus here? I should, right? Yes, I should have a minus here because I have exponential.
Okay, yeah.
Yeah, I should have a minus here. Okay. Okay, so all right. So this is a pretty important equation, almost as important as this one. So I'm gonna right here, circle this out. Okay. And of course, you can write the same for E2. But I'm not going to be bothered by that because the same arguments apply to E2 too. Okay. I want to point you to this. You see the first term? This is an oscillator. Oscillator, harmonic oscillator. You see this harmonic oscillator equation? right? Okay. And this is the drive. And we call this a parametric drive. The name is a bit strange because parametric kind of, is associated with parameters, but what's the parameter here? It's kind of strange. Okay, I'm not going to go into the detail of that. It comes from historical reason. It doesn't really mean anything here. This is just not, here it just means a non-unit drive. Okay. Now, you see the fun. Okay, so you see now here, since it's an oscillator, I need to have a drive, a cosine. I need to have a cosine omega 1 t. So this drive train better produce something like this in order to be resonant with my drive, right? And so that I can like excite this field. Yeah. And how are we gonna go get this? Well, we know here we have a cosine omega 2 times the cosine omega p, right? Inside the bracket. And cosine omega 2 and cosine omega p is basically this times right? Yeah. So only 2 terms can possibly give you omega 1, right? Okay. Let's try. So if this term gives you omega 1, then that means omega p is the sum of both. Okay, that makes sense, right? Because in our experiment, we have a high energy photon and they produce 2 lower energy photons. That makes sense. How about the other one? The other case. Omega p is now the difference frequency of that. Okay. Well, can this work? Well, first of all, if these two are, let's put it this way. Your input, let's put it this way. Your input is omega p only. Yeah? And your output is omega 1 and omega 2. So from energy conservation point of view, right? Whatever your output photon is, it should not have energy higher than the input. But in this case, omega 1 obviously has a higher energy than omega p. Right? So this is also not the case that we're interested in. Okay? However, can this mathematically work as a resonant drive? The answer is actually yes. Okay? But the context is, in this case, will be very different. It's not what we're interested in. So I'm not going to waste time talking about it. Okay? This is what we're interested in. one high energy photon produce two lower energy photons instead of a lower energy photon and a high energy photon. Okay? Yeah, so this is what we're interested in.
The second one also we can produce if the crystal has some excited states.
What this will do is to exchange energy between the field omega-1 and omega-2. I actually wrote a paper about this. It's called, what I call this is a difference parametric amplification, and this is optical parametric amplification. This exchange energy, this convert energy. Okay, so but let's not go into that. All right, so all this very lengthy mathematical discussion is just to establish that the interaction here has a resonance nature. Resonant. It has a resonance nature, and it's actually a resonant excitation. You can think of the field. Let me just give you a physical picture of this. You can think of the field, the input field, from vacuum, E1. So this is W1. W1 from vacuum. I'm sorry, this is W2. And this is W1 from vacuum. Okay? So we have a little fluctuations from vacuum to start the field. Okay? So that gives us a non-zero initial condition to begin with. And then through this resonant excitation, this energy gets dumped into this modes. Okay, and it amplifies the vacuum field. Okay, and that's what we're seeing here. Okay, so it's a resonant excitation, and it's called parametric excitation. So that's the fundamental physics mechanism for this SPDC generation. Okay, so I think it's important to get that clear out, because the rest of it is pretty just technical details on, like, this is physics, and the rest is just like, how do you choose parameters in your experiment, that kind of thing. If I just give you that, then I don't think you will have any understandings on what SPDC is. You just like assume it's some kind of black box and you need to choose parameter to make it work. All right, but now I've given you this, and this will make everything else, discussion of everything else easier. All right, so let me go with number 7, and hopefully that's the last. Hopefully that's the last one. We have spent a lot of time set up the stage. So hopefully the discussion from now on can be much faster. Okay. All right. Okay. So we talk about this process. A photon come in, after interaction, 2 photons come out. Microscopically, it looks like this, although we were using the classical electrodynamics. but a microscopic picture looks like this, right? In this process, we see that two conservation laws needs to be obeyed. One is the energy conservation. Therefore, we have h bar omega p equal to h bar omega 1 and h bar omega 2, correct? Now, we also have the other one. So this is the energy conservation. So we also have another one, Kp, K1, K2, momentum conservation. Okay. All right. Now, although I'm using a microscopic picture here, these two condition, okay, if you can remove the h bar, right? If you with the h bar is called energy and momentum, but if you remove the h bar, it's just basically a resonant condition. Omega p equal to omega 1 plus omega 2, which was in the equation that we just discussed. And here you also have Kp equal to K1 plus K2, right? This is called a phase matching condition. And in the previous discussion, for the sake of simplicity, I used this spherical wave as its mode function. So we just have the K. The K derivative was like removed. But if we start with the most general form, then you will see that this also needs to be matched. So both conditions, frequency, resonance, and phase matching, all exist in classical electrodynamics, just in different language. Okay, so I want to see that this is not something it's not required by quantum optics. This condition is not required by quantum optics. It was already there in the classical electrodynamics. Okay, but now I want to just stick with this language because it's more intuitive, talking about energy and momentum. Okay. Now, I think suppose if we just consider the collinear case, Kp, K1, K2, right? Then this equation pretty much implied this equation. Correct? Because I just put this over C, this over C, this over C. And that's this, right? But is it really? Is it really? Don't forget, we are in the material. Okay, so in the material, everything goes with Maxwell's equation in material. And your K and omega are not related by C, but they are related by what? V. So, so let me write this down. So now since they are related by, okay, so let me just cross this out, okay? Let me write them as this. Let me write pran. Pran just means that this is the momentum in the material, okay? So you need to take into account of the index of refraction. That's the velocity of light in the material. Okay, what does this mean? This means if this will be the same, okay? Let's just assume for now that these are the same because we said that this is 405 and this is A10 and this is A10, right? Okay, so let's just assume for now that we have, so let's call this omega naught and this 2k naught. Okay, let's just for now assume that this is the case. Okay. This has no problem. I know we can do this. There's no obviously logical problem with this. But now, if we look at this equation, right, and we know this is related to this equation by this dispersion relation. This is called dispersion relation. The reason it's called dispersion relation is because this V is different for different wavelength. Okay, when something is different for a number of, when something changes with a certain parameter, we usually call it dispersion. Okay, in the context of a pulse, of course, that will cause the pulse, some pulse component, when you have a pulse, right? Okay, really the name of dispersion comes from a pulse falling apart, because a pulse usually has many frequency components, and some components travel slower than other components, since this velocity is wavelength dependent. So when they travel in vacuum, of course, they all travel in the speed of light. So all the components stays in sync, and the pulse remains its shape. But in the material, some components travel slower, and the red travels slower, the blue travels faster. So your pulse start to fall apart. Okay, and we call this the pulse is dispersed, like spread out. Okay, that's really how the name comes in. But here, let's just focus on this. Here it means K omega P, this is equal to omega P times N P over C, and this is omega 1 or 2 omega 0 times N naught. Okay? Correct? From this equation, we know that, of course, this part is correct. Right? So we don't need to worry about this. This is correct. They cancel. What gives us problem is this. We know that this index of refraction depends on wavelength through something called the Selmayr equation. Selmayr equation. So let me write it down. Selmayr equation. Selmayr's equation, and it basically goes like this: 1 coefficient, 2 coefficient, 3 coefficient, 4 coefficient. It goes like this. Okay? Pretty ugly. But it's pretty much just a monotonically decreasing line. A little bit like 1 over lambda. Okay? So that means every wavelength will have a distinct value of index of refraction. Therefore, if lambda p is 405 nanometer and lambda naught is 810 nanometer, then this equation cannot stand. There's no way, right? This is 810. This is 405, right? Obviously, they are not the same. They cannot be the same. Right? You have this difference. Okay. This difference we call it phase mismatch. Okay. For other reasons, but anyway, this phase matching condition, this momentum conservation condition, cannot work in the material unless you have different index of refraction for P and for this 810. Unless your input and output light, okay, for some reason they have different index of refraction. Otherwise, this cannot work. Okay, that's why we go to PBO. BBO, beta BBO is something called birefringence material. Okay, there are two types of index of refraction depending on the incident angle of the light, the polarization of the light, etc. Okay, so there's something in BBO that allows two sets of index of refraction. Okay, two sets, and one is called ordinary and the other is called extraordinary. Okay, one is called ordinary and the other is called extraordinary. Okay, the reason it is called ordinary, of course, both look like this. The reason it's called ordinary because it has a larger value than the extraordinary. A larger value of n means what? How does that affect the speed of light?
Decreases.
Huh?
Decreases more.
Say again?
Speed of light decreases more.
Decays? No, it does not decay.
Decrease.
Decrease. Yeah, thank you.
More.
So this means slower. So slower light speed in material.
This is also in case of quartz crystal, right?
Huh?
In normal quartz crystal, quartz prism, we also do these kind of experiments.
Yeah, of course. Everything follows this Semi's equation. I'm just explaining why one is called ordinary and the other called extraordinary. The ordinary one, of course, gives you a slow light speed in material. This is expected. Okay? But the extraordinary will give you a light speed that is closer, still slow, but closer to the vacuum value. It travels faster than what you would expect. So this is faster. Faster than ordinary. Okay, ordinary is what you would expect from a normal material. Extraordinary means it will go faster. Okay? So birefringent material has two sets of index of refraction. And if you can, for some reason, make your 5 nanometer go work with, if you can make the extraordinary apply to your 5 nanometer and your ordinary apply to your 810 nanometer, then you have a match. Then you have a match. So that's pretty cool, right? And that's awesome. We like that, okay? So that's basically the idea. Okay, but how it actually works is more complicated. Okay, and of course, it's late now, so we won't go much into detail, but I just want to motivate you with like why we use this thing and why does it called and why is this nonlinear. Okay, and there's another thing about its nonlinear nature. We'll talk about briefly later, but like this mismatch in the index of refraction is the main motivation for us to use something that is birefringence. Okay. All right. Now, just a little words about birefringence. Like, how does it come?
Is this mismatch different from the mode mismatch?
Huh?
Mode mismatch is different case, right? Not this case.
Mode mismatch is like a more general concept. Mode mismatch also include this phase mismatch, but mode mismatch also include the intensity profile. So if you have a Gaussian and you're trying to, for some reason, you try to match, if you have like a every disk type of profile and you try to match with something with a Gaussian profile, for example, in the cavity, that this intensity profile matching is quite important in the optical cavity. So there you need to consider both, and of course, in that case, you are in the vacuum, so you don't need to worry about this momentum, right? But if, say, the cavity is like an embedded cavity, like a microcavity in semiconductors, then you need the mode matching will include both the intensity profile and the momentum, okay? Because remember that mode function I drew for you is exponential ik, and that includes the k, right?
Yeah.
But if you have a lot of k, that also gives you the intensity profile. So mode matching is a more general concept that has two parts. That has two parts. Okay. All right. So I want to just briefly talk about how birefringence comes in. Okay. Let me just use this example of BBO. Oh, I prepared this very nice pictures. First of all, I want to show you the real crystalline structures of BBO. It looks like this from top. If here is a BBO and you look at from the top, the so-called C-axis, okay, it looks like this. It has rings, and these rings are the borite. The boron and the oxygen together makes these rings. Okay, and the baryon are the green ones. Okay, and of course this together they have a crystalline structure, but in terms of this the fundamental unit, I'm not talking about a unit cell, I'm talking about like the fundamental unit of the atomic structure or the molecular unit. It is like this, like a ring. Okay, and this is what you see from the side. Okay, so they are just planar rings. Okay, so for borite, you have all these rings. It's like donuts, and they are all stacked up in space. Yeah. So you can imagine that when. So let me just write donut rings. Okay, draw donut. So this represent borite rings, and they are like stacked. Not exactly like this, but this gives the idea. These are the borite rings. Second, here. Borite rings. Okay, so this is like plane 1 and plane 2. Okay. Now, when you have the field that come in this direction, if you have the light coming in this direction and your field is parallel to the plane, right? The electrons are easily disturbed. They can be disturbed easily.
In the plane.
In the plane, in the ring plane. Okay, because it's shared between the atoms, right? So I mean, they will run in there anyway. So when the field comes in and is shaking, like here we're not talking about like an atom. The previous picture that I show you is like one atom with electron cloud. Now we are considered a little more complex structure. We have like atoms, and they are wrapped by this electron cloud jacket. Okay, and this jacket can be most easily moved in a plane that is defined by this ring, this nuclear rings. Okay, but if you come in this direction, so if this is like a crystal, right, and you can shoot lasers from different directions, from this side, or from this side, okay, then here you with this you just drive the electron left and right to get induced dipole moment. But with this, you need to drive the electron up and down to get induced dipole moment. This is a lot harder. Okay? To drive it up and down out of plane is a lot harder than drive it in plane. Okay? Therefore, light going from this direction interact with the atoms, with the boron rings weakly, because the electron does not respond very much. They just kind of, I don't really want to move. This is my happy place. Okay, I don't want to move this way. Okay, but when this comes, oh, electrons are very happy. Okay, they just move left and right. Yeah, so the interaction between light and material is stronger if light propagates in this direction, and it's weaker if light propagates in this direction. Now, if light interact in the vacuum, light doesn't interact with anyone, right? So you just go like, shoo. But when light interact with something, yeah, when light is interacting with something, it is, in the microscopic sense, it is absorbed and re-emitted in all directions. Absorbed and re-emitted in all directions, right? In the microscopic sense. So you can imagine when we have a strong interaction, then the absorb, emit, absorb, re-emit, absorb, re-emit happens many times. And this process slows down the light because it's kind of busy being absorbed and re-emit, being absorbed and re-emit. But if this goes through the material, pretty much not interacting with anyone, okay, it does not need to be absorbed and regenerated, then it can go pretty fast, just like it is in the vacuum. Okay, so weak interaction, strong interaction, this implied slower light speed in material, and this implied faster light speed in material. Okay? Yeah? And in terms of this terminology, we call this fast extraordinary. and we call this. Oh, I'm sorry. Let me just write it with blue. Call this extraordinary. And this is ordinary. Yeah. All right. So that is thin. Okay. Now, if you come in at an angle, right? Then you have. If you come in at an angle like this, right, and your polarization is in this direction, then you will have a projection, a horizontal projection, which moves the electron easily, and you will have a projection on out of plane, right, which does not move the electron easily. Yeah. So these two projections will bring in, will both affect, will together determine the speed of light. Okay, here you have a strong interaction, here you have a weak interaction. Yeah, so the speed of light now is determined by NE and NO together. Okay, so I think that's what pretty much all I want to say. Okay, so in the most general case, so let me just draw a material. Okay, if I have light come in, and this thing, okay, I cut my crystal in a certain angle with respect to this axis. Okay, so this axis, this spatial axis, I call it optic axis. Okay, it's just a name. Okay, I call it optic axis. So this is optic axis. Okay, if I just choose to cut my material at with a certain angle, so this is a certain angle, okay, crystal cut angle, then and so that my normal incidence will make an angle with optical axis at a desired value, okay, and let me say this design value is 29.13, almost 30 degrees. Okay, then you see in this case, so this is what happened in our experiment. Our experiment have this crystal cut angle so that when you have a normal incidence, this is making an angle with the optical axis at almost 30 degrees. Okay, so this is not perpendicular, this is not parallel. Therefore, your MP, so let me write your MP, so the light inside, okay, so this is C, and here you have V equal to C over MP. Okay, so your MP now is a mixture of this is like almost like a projection of the ordinary and extraordinary index of refraction. Yeah. Okay. So that's this. You can see if I have my light propagate, if I shoot my light like this, okay, so that ignore the, so if I correct for the reflectivity, I shoot it at an angle so that inside it is parallel to the optical axis, then this P, so if I don't do a normal incidence, if I just do that, then this delta theta P is 0. Then I will have only the ordinary index of refraction contribution. Okay. All right, but now I'm doing normal angle, so I have a mixture of two. Okay, and the polarization I'm gonna choose is this. Okay. For some reason that we don't need to explain here. And for the P, for these guys, in general they don't need to be collinear. It will turn out that if you choose your polarization to be like this, it will turn out that the output frequency, the polarization will be in plane. Sorry, will be out of plane. They are perpendicular. And by the way, this is called a type 1. Type 1 nonlinear crystal. Okay, type 1 parametric down conversion.
BBO is type 1.
Type 1, yes, type 1. Well, not that BBO is type 1, but like this particular setup that generate the light to have both of them the same but perpendicular to our input. This is called the type 1. Okay, and of course they are type 2 and stuff. You can also use BBO for type 2. Okay. So the nonlinear optics has so many parameters. So whenever you change your configuration, there's a new name for it. Okay. Okay. So since they are like this, right? If the optical axis is like this, then the plane is this, and if the polarization is like this, that's in plane. All right. So that is ordinary. Okay. Okay, so these are the index of reflections for the light using a birefringent materials. Okay, and now since I said that there is really no need, we can have a more general construction of, you know, the length doesn't need to be the same, the angle don't need to be the same, right? And this is omega 2, K1. K2. This is Kp. In this more general configuration, we write, of course, this still the same. The energy conservation gives you the omega p equal to omega 1 plus omega 2. But for momentum conservation, we have we have two projections. We have the vertical, we have the horizontal, right? The horizontal is, of course, Kp prime times cosine theta K1 prime. And this prime means it is in the material. So you need to include the index of refraction in the equation. K2 prime. And we also have sine K1 prime. The vertical momentum for the two photons needs to match, to cancel actually. Okay. Okay. So this is the most general setup for the SPDC generation, to satisfy the phase matching and to satisfy the resonant and phase matching condition, which was found out the equation, the Maxwell equation we just gave. And these are the related index of refraction formulas for then. So anyway, these are pretty much everything we need to understand how our experiment works. Okay, and here I'll give you this is the last one. Here I'll give you
It's possible to have 10 minutes break before.
I'm gonna get done really soon. I'm just gonna give you a few examples, and I'm just gonna write numbers here, and we're done. And then we can have a break, and then we'll do the discussion. Okay. So just bear with me just a little bit. So so if we want to know, so if we have lambda p, okay, and we know it's, so we can rotate our crystal angle, so we also know p. So given lambda p and our crystal rotation, right? If I want to know, and suppose I know that I am expecting a certain frequency out. So say this is A10. Okay, but I do not know what angle it will come out. I also do not know what the other frequency will be, and also its associated angle. Okay, so given lambda p, theta p, lambda 1 and phi, theta 1, theta 2, and omega 2, lambda 2. Okay, so usually you, so this is the program, and then we use that equation to do this. Then we will find, but this needs to be found numerically. We will find that except case 1. So this is the standard case that's working in our experiment. We will find that 2.913. Okay, this is beta BBO. Okay, this polarization is like this. This is for 5 nanometer. Okay, and this is A10. We will find that this, first, of course, this is in plane polarization. We'll find this is 2.9847 degree. And the other one is also the same wavelength at 2.9578 degree. Yeah? So this is the case when you have equal energy distribution to the two photons. Because you see this is wavelength is double of this, so that means the frequency is half. There is also another case where you have collinear, but in order to have the phase match working, here your angle needs to be smaller, 28.7. So you see a little bit change can affect things a lot. So here is, let me just draw this. So this is collinear generation. Okay. Okay. Now, you have go from this to this. What happened in between? So this basically is a ring, right? Because we're only drawing this, but you can rotate the whole thing. So this produce this not in two rays, but in a ring of rays. And these two pair of rays are correlated. These two pair of rays are correlated. These are correlated. These are correlated, right? Okay, so it's like this. Okay, now going from this to this it's almost like closing the angle. It's almost closing the angle so that they are parallel. Okay, so what happened if we have, so this is 29.13 and this is 28.7, right? If we have a case where the angle is in between, okay? So case 1, so this is the standard angle, standard, okay? And case 2, this gives you collinear. Okay, so if we have something in between, yeah. Let me just drop this by a little bit, 20.9, okay? So it's not just kind of in the middle, sort of, 29.9. Okay, so here, 29.9, 29.0. Then this will give you 2.4778. 2.4778. Okay. So you see, when we rotate the angle to make it to, when we close the angle between the optic axis of the material and the propagation direction of our input light, the ring radius also goes down. Ultimately, when we reach this angle, it doesn't take much. That the ring is like just one spot. It's not a ring anymore. It's like one spot. On the opposite, we can open the angle, and the ring will just grow larger and larger. Okay, so that's one of the experiment you're supposed to do in the lab. By changing the crystal angle, you will see the disc opening and closing. All right. All right. So the last case is case 2, case 4. What if we have, so far we have talked about like energy equally distributed on the two rays, right? What if we have energy different? So if I want to go for, if I want to go for a standard angle, if I'm at a standard angle, okay, but I want to look for an output wavelength that is significantly higher than this. So say 760 nanometer. Okay. What would this angle be? Would this be smaller than this or larger than this? Okay, we don't have much time, so I'm not gonna make you guess. The answer is it's smaller. It's smaller. The higher energy photon is closer to the center. And that means the other one will be a lower energy photon, lower energy compared to A10. Right? It will be a lower energy photon, and the angle here is larger, 3.3929. Okay? So you really have like a disk. And at the equal radius, at the equal symmetric position, you have the same wavelength, A10. But when you go in, you have higher, and that a higher energy photon, and that will be paired with a lower frequency photon at a larger opening angle. So that's what fills the inside, okay? But you only have a symmetric ring for the there's only one wavelength that will give you a symmetric ring. The others are just like higher energy photon match with pair with a lower energy photon outside the ring. Okay, so that's the how it work. All right, so that's everything I want to tell you about. Okay. All right, cool. All right, take a quick break to drink water, and then we will quickly go through our quiz and give you some points. Hopefully. And okay, and then we move to the lab. Today's quantum spin lab is very, very interesting. Incredibly interesting. Even more than the Ramsey.
You say so?
Yeah.
Maybe.
And Mustafa, do you know if David has his data for presentation? He has not show up for 2 weeks in a row.
I him last week and he has not responded.
Yeah.
I messaged today.
And the presentation is in pretty much in 1 week actually. Like
yeah, one
almost like a little
2
bit
days less than
yeah, a little bit more than 1 week.
Yeah, and
I'm a little worried about him.
Yes.
And also Tom, I don't think he has his data yet.
But is Tom choosing the presentation route?
Everybody choose the presentation.
He told me in the first lab he was planning to choose the theory route.
No.
I didn't know.
No. Everybody choose the. Well, if he choose the theory route, he has not submitted any report so far, and it's almost midterm.
Yes. He said he's a bit scared of presenting in front of everyone.
Yeah, that's why we have this, because this is unavoidable. Okay. All right, 1 more minute. All right, so you see the question now on the board. Would everybody please stand behind the answer of your choice? Does the input light in spontaneous parametric down conversion come from the vacuum field? By input light, I do not mean the pump light. I do not mean the light that gives energy. Okay?
You're thinking about the pump light. Yeah.
I'm not talking about the pump light. The pump light is 405 nanometer. That's not what I'm talking about. That's not the input light.
No.
Okay, the input light refers to the equations that we give in the Maxwell's equation. Those are the light that we're interested in.
Like where E1 and E2.
Yeah.
So not the laser light.
Not the laser light. Yes. Okay.
It's like it's a, when you say like that, is it like
Okay, Phoenix, move. I don't mind you guys do computers, but please sit at the front. That's my only asking, okay? Sit at the front, okay? Yes, no, okay, great. So we have two different opinions. You will talk with Phoenix, start with your round, and you will talk with each other. Mustafa?
you are you can read
You're wrong because you have not read. You have not read the question.
maybe because then she needs to read it again before she's ready to defend herself.
You're wrong because you have not read the question yet.
I'm gonna tell you why I'm right. So the input light is
Yeah, I think you're wrong because
conversion.
I think maybe
So yeah,
again, I don't remember it now,
the extra
but I still think you're wrong because
the moment
because like
and the energy
I think
conservation.
we talked about you
So
still
extra energy
need something to store
after
the process.
if it's bigger, it would have
So
come
it's
from
no, right? Right? When
No,
they
no,
say
no,
it's
no,
all
no.
right.
It's like it's like I
already-
think it's I would guess it's like similar to spontaneous emission. Like it comes from a vacuum field, and
This
then
is like it's made of
Yeah,
pressure.
but
Phoenix says he's wrong. You're wrong.
Okay, you're wrong.
Yes, good. See?
The wave pressure.
the input light is the
But
yeah,
it's only written on the table, where it tells you that the just only the one different from the
no. But,
big
Inside the
field
cavity, the
can
mm,
write the
yeah, it's all because of
resonance.
fluctuation.
Do you remember there's a
yeah.
but for the set one you cannot because
But isn't it like you still need the first vacuum to like get starting, and then you use the pump like to drive the.
but now you don't have, right? So you cannot have the
yeah, I would say like apart from the pump of the laser, we don't have
SPDC.
30 minutes, 30 seconds.
That's reason.
That is the
But
only
this is-
thing
Because
that
last time
adds
I
to the
just
system.
reviewed
Yes.
they
The rest is from vacuum.
Yeah.
Vacuum field.
But the input light is the.
Yes, you need to like to generate the spontaneous parameter without conversion.
Yeah.
Can you just use only the input light, but it's come from the vacuum field only. It's like a cell. E1 or E2. It's like that.
Okay,
Because input
Thumbs
light
up.
is not EP, right?
great. All right, go back to your line. Now, anybody want to switch side? If not, then we switch partner and we do this again.
Yeah.
Okay, you will debate with Phoenix and you will debate with Mustafa. Mustafa.
You are wrong.
Okay.
Good.
Why am I wrong here?
Because
You are right.
what is the
I get confused again because you said the
What-
input
what's-
light is not the light from a
Not
laser,
the
it's
pump.
the light
So
that
what
it's
generates
speed?
E1 and E2.
Yes.
Exactly. Okay. But didn't he say in some time in the lecture that we have the equation and then of course you need the pumping light to have this happen. And didn't you need like the vacuum field to store?
Say you're
the
wrong, you're wrong.
information?
Yes, exactly.
Do you also remember that?
Yeah, means like he is
in
the laser
order
light is
to
outside
have
the crystal. He's talking inside the crystal at the angle of the 2.8 dB.
Yeah.
There was like yes, not 2.8, 29.15
do
dB.
you remember
That point. I think that come from some part of vacuum field, and that's why
Yeah,
they
yeah.
Just can be right.
because that's also
Yeah, yeah, that's why I remember last time we had some discussion about the constant and the standard. And choose
But if
only
it's
the
a pumper
constant,
light,
we can
pump light
do the task.
starts with vibrations. Why would do you say that it comes from the vacuum field?
And the center is safe.
that's the vacuum field before.
So if you just consider
No, but didn't the laser, the pump light create that vibration?
Yes, from like also is helping me.
Maybe.
30 seconds. Go, 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 go.
But I don't remember exactly what the equation said, but I thought like we needed the vacuum field to. It's like when you start.
So, for example,
Like, I'm not sure it's no, maybe I cannot say. I was thinking it's the same as like continuous emission in some way. Like when you start a laser, you need one to get started, and then maybe I'm misunderstanding how to do the equation.
No, I don't think it has nothing to do with the lab. It's just inside the crystal when this process.
Yes, good. You are trying to. I see that you are shaking his belief. All right, good, good guys. Let's get back to your line. You have collected enough information. Anybody want to switch side now?
Can we get one more discussion round?
All right, let's do a 1 minute discussion. Just find a random partner and discuss. Okay, then you two will do. Then you two will.
You're wrong.
All right, so I think you're wrong. Saying yes.
Because
Why did you think I'm wrong? Because you were in my line also.
Yeah, because out of further arguments, yes, it's hard to say why you're wrong.
Yes, crossing is not even if.
And of course you have the equation, right? You put in the different parameters. I see that doing some
Which equation?
like the 2-1 from the not the micro but the wave
It
equation.
comes from. He's not saying it's only from.
Quite a lot of.
30 seconds.
we just like come from the
Where you
computer.
put in these things.
And
yeah,
you can do
okay.
that.
It has a contribution from the
No.
Good, Phoenix. I see some momentum. No, you're wrong.
I'm not saying everything is produced from the vacuum field. It has the pump part and the vacuum part.
So you need that to kickstart the
Yeah,
process.
but if you just only have one.
But you
There
have
is
to
no
see it in
only.
a different way.
10 seconds.
No, no. Because he don't pick it up.
Yeah. We're getting ourselves some scientists here.
So is there only here?
Huh?
Is there only here? Only comes from
No,
vacuum
but
field?
the thing he
There's
just
none, right?
mentioned about last time he mentioned is just like no pump at all.
No pump vacuum.
No. I'm talking input light does not mean the pump light.
No.
There is pump. There is pump. There is
Yes.
405 pump.
Yes.
Okay. Input light here, I mean for E1 and E2. Okay. There is pump, of course. You cannot start with no pump. Let's pump. All right. Good. So you have gathered 3 rounds of information. Okay. All right, people. Let's get back to your line and let's do this again. Anybody want to switch sides? Okay, great.
I'm not sure. Hey!
Okay. Woo! All right. This is working for people. All right.
Don't say no, it's right.
Ayya! Correct. Congratulations. Okay. So
I'm still confused about
it's okay.
Yeah, can you explain it?
It's
to me?
okay. You
Can
are.
I get additional point?
You see, you're getting additional points for sitting here for so long.
Can
All
I
right.
get additional point to taking on?
No, no. Let's call it agent speed. All right. Okay, I want to say, see, the
You
pump
can pay me
in the equation. You remember the pump field look like this. The pump field look like this.
Yeah.
If E2 is 0 to begin with, absolutely 0 to begin with, there's no drive. So there must be something. And that something, in the case of spontaneous parametric Dunn conversion, that something is from the vacuum fluctuation. But of course, you can input a physical light. And then using this, omega, so you can, instead of input omega p only, you can input omega p and omega 2. Okay? And use that to increase, to even amplify omega 1 to a higher level. And in that case, it's just called parametric amplification. Okay? So spontaneous parametric Dunn conversion is a special case of parametric amplification when the input light is only the vacuum field,
But
not a
still,
physical laser.
This one is the main power comes from
Yes,
this one.
yes.
So this is like
But this
starter.
cannot be 0.
That's why
You need to have some value. So that fluctuation, that instantaneous fluctuation from the vacuum field is sufficient. So that's the magic here. Isn't it cool? So you're like doing vacuum field physics. Okay. So the second question is not hard, but if you need to pay attention to the lecture. So in order to answer this question, does the second order susceptibility originate from anisotropic electron bonding? This is very mouthful words, but basically this says the same thing as I say in the lecture. Okay, I just use a slightly different language.
But does it means it has means if I said no, does it means it has no contributions, or it's just mainly from this?
I don't know what I'm talking about.
You mean like the second order? Is it only from the
Anisotropic electron bonding?
partly?
Yeah, means it can
I
due to that.
I'm not answering your question. Okay, I think this is well defined enough.
If it's mainly from that,
Or just
Yeah, I
say
think
in the context of our discussion today. Okay, let's limit it to that. In the context of our discussion today, does the second order susceptibility originate from anisotropic electron bonding? Okay, so that's first round. Choose an answer. No, yes, doesn't matter. Just choose a line, please. Let's save some time. Phoenix, go. Don't think. Just go.
I'll think later, just take
You will think later. Okay, you will think later. Okay. All right. So you choose no. You choose no. You choose yes. Okay. Great. Even distribution. Okay. That's debate now. Okay. Musfa and Simon and Vida with Phoenix.
Okay.
Yes. Good. Good. You're wrong. Good. Always start with you're wrong.
You're probably right because I didn't think about this properly yet.
I haven't thought about it, but I
Okay, so
think
you say no.
it is not from the second order.
Defend your answer.
Can have some parts, like,
Don't comply.
the main reason is not that.
Do not comply.
Why? What's the main reason?
Defend your answer. Do not comply. Because you might lose your point.
Okay, no good answer. Yeah. Good. We'll come to our side.
Well, then you should ask him, do you have a good answer? You're wrong. You're wrong too.
Can you explain how you interpret that type of electron binding?
That's what I'm trying to say.
Yeah, because I was got confused which one.
At the last part, you are talking about that.
Isotrop. Okay, let me explain what isotropic electron bonding means. if you have an atom here, and this atom is sharing an electron with other atoms, okay? If this sharing strength is the same, of course it's discrete, but pretty much in the same in all directions. Okay, there's no preferred direction to share the electron.
I see.
Then it's called isotropic electron bonding. Okay? All the same. Okay? Equally good. It's called isotropic. Okay. All right. So that's so time's up. Do you okay? Go back to your line. Anybody want to switch? Okay, good. We still have 2 versus 2. Great. Now we have Vida and Simon, and Nusfa and Phoenix debate.
Yeah.
Okay, I think you're wrong. What would it otherwise come from?
Isn't that the first order? Or is the first order just the like, let's say, priority thing?
You tell me. I think it's second.
Oh, yeah.
The isotropic doesn't mean each direction is different. But
Because I'm thinking,
for us,
what's
he
causing the
said
first
that
order? If we start from that end. And
with
then,
respect to
in that end,
we have
okay.
rotation in this direction.
I don't remember exactly which one was
Here
which.
we have rotation in this direction.
What could cause,
It is like equal.
like the most simple phenomena should cause the first order, right?
We don't.
And then the second should be a different, like a second hand interaction or something.
These
Or
two have some
for
differences.
some effects. So if you say that this is the second order, what would be the first order?
We take it as like this, all will be going in the same.
Or could you say that the first order is the thing that is like
this one is not isotropic. It's all the
like
same.
the first order could be that means that they don't have any.
Anisotropic for me means if you take 2 of them,
I don't know, but I don't think it's because of that.
that is how we drop up like
What would it be instead?
the
I don't know, but it isn't.
in a molecule there is always one bond is bigger than other.
Yeah.
But overall we can see.
So your defense is you don't think it's from this one. Not that I have any better defense.
You consider it's like the center is like
30 seconds.
and you have like many electrons like
Yeah, we have that in.
yes, you have many bonding here and like
Phoenix is picking up. Yes,
Different.
good.
I mean for different extremely different
What other things could we have that could cause
state.
stability?
It's always the case.
10 seconds.
I guess
For the anisotropic,
electron.
it will be different. That's for isotropic, it will be the same.
I-
No
I-
matter the same
like,
direction.
if you look at one atom, electrons should really be the same.
Hands
right?
up.
Yeah, it's
That's
like,
our
And
point.
if
Hands
you
up.
have, multiple,
Different for different systems.
Okay, good. Okay, your job is to collect information, not to bring other people to your side. Your job is to collect information, and you need to decide for yourself. But you do it in a way that you try to convince the other person. Okay, but it's really convincing yourself. Okay, so go back to your line, and if you want to change your line, do it now. Nobody? Do we need another round of discussion?
I guess we need one more, yeah.
Okay, I'll give you 1 minute. Okay, just grab a partner, whatever.
Okay.
So the
Yeah.
same for the
What
as
means
here
from
we
that?
have
It's
zero
not only the
isotropic.
If you take different rings,
For
in our case,
so, okay, what are the rings?
this you have the ring structure, right? For the molecule.
Yeah.
Any direction.
Yeah, I see.
The two
That's
or
for
4 rings.
isotropic for different direction.
So it has like a cloud structure. This goes on. It will have some differences in the
you get
all
different
the
results
different rings.
according to which
With
direction.
that difference, if it is
Yeah,
producing, it
I
comes from
agree.
the anisotropic.
But then I'm
But it has
not sure
similarities.
because it's the
If
second
all
order.
of them are little similar,
This can
it
be
comes from.
more order than
So, but
like
what we have, if the light comes from this direction,
Yeah, exactly.
all those will be
But
That's
acting
just for
on this
linear order,
direction.
it's ISO.
All the
Yeah.
It's a linear order.
If I
so
change this
but
direction,
if you think,
all the electron cloud will be moving on this direction.
but wouldn't it be like
30 seconds.
zero order? That's
If
isotropic.
it is like there is like some other
Wouldn't it be
disturbances
like
or all of them are
zero
moving the same
order?
direction, it becomes
Yeah,
isotropic.
that's the isotropic
That's what
case.
I think.
And then if you start adding this, the first
From the
order
explanation I
is
got.
anisotropic.
You say it's no.
No.
Okay. What would the second order?
And then the second order, maybe it's on the same
It's
phenomenon,
not isotropic.
or maybe it's
All of them are moving
somewhat
the same
different.
direction.
Yeah.
But he did draw it out like
The light
first,
comes
second,
from
third,
all
right?
of them move.
Oh, yeah, it's, yeah, for sure.
So
Yeah.
I think that's like the
All the
isotropic
places.
electron.
Yeah. I guess if you write out,
It's
So
not
just the orientation.
if you wrote out,
of
do
the-
you remember where like or you can say that.
no.
But
The electron
in this
cloud.
context,
Orientation
we should
is
consider
this
that
one.
Yeah.
With the direction of
because
the light.
if you
10
the
seconds.
electron moves.
there's a sensitivity
Means if
in
it
this
moves
data,
randomly
come from
or
some
different
other,
directions, this
extra,
in this crystal it moves like this, in this crystal it moves like this.
external
Then that's
Yeah.
like
fields
an
that
isotope
should
for
be
me.
originally
That's what I
from the same sector.
Yeah.
And
What's
on
your-
zero is about
But he did like something like this, right? I don't remember exactly.
Hands up.
Yeah.
All right, guys.
Or it's something different, yeah, but
Go back to your line. Time to make up your mind. Anybody want to switch side?
wait.
After 3 rounds of very intense debate, by the way, I really like it. You guys are doing much, much better than 7 weeks ago. Okay? Now you have more confidence, and then and then you try to like give good arguments. I like that. And you're also very polite. Respectively say you're wrong. I like that. All right. Anybody want to switch side? Okay. We're staying with your sides. 5 more seconds. 1, 2, 3, 4, 5. All right. Done. Answer is yes. All right. So we have Phoenix and Vida. All right. So in principle, like I said, when electrons are pulled really, really far away from the nucleus, there is of course nonlinearity and thus the second order susceptibility, right? This is basically a synonym for nonlinear response, right? Okay, so yes, of course, this is universal, but in the context of like when we talk about materials, like which one is regular crystal and which one is can be used as nonlinear crystal. When we talk about that, you really need to consider the electron bonding not just to one nucleus, but like also the surrounding nucleus. Okay, and there you have this additional degree of freedom that comes in if the bonding is the same in all direction or not in all direction. In the example of the borate ring, right? It's bonding in this plane. The bonding is in this plane, so it's shared between nucleus in this plane. So therefore, it is easily moved in this plane. When you try to move it in the other plane, it's stiffer. Okay, so in this case, the nonlinearity comes from the ice from like in one direction is stiff, the other direction is not so stiff. In the most universal case, like I said, when you displace it far enough, it becomes stiffer. So that transition from not so stiff to stiff, there was from displacement, but in terms of like crystalline structure, that is the direction. You have stiff here and not so stiff here. Okay.
Is it the same for third level?
Huh?
So every level is due to
Yeah, every level is slightly different, but the third order, everything from after the second order is nonlinear. So they all have to do with some anisotropic bonding and not stiff versus not so stiff. Okay.
And also the first, or
First is no. First is the linear response. So that's when
It's
you
just the
don't move
same.
it very. So in order to activate the susceptibility, you need to first drive it really hard. Right. You need to drive it really hard, and then you will see if you have strong susceptibility or not.
I see.
Yeah. Okay. All right. So, but the first order is the weak, the limit when you have like a weak drive, and there it doesn't really matter. It's just like okay. Effectively, everything is symmetric for the electron because it just barely moves. All right. All right. Thank you very much for your participations, and congratulations on Phoenix and Vita. Okay. All right. So we will move the lab today.